Let's look at exercise 3. Here we're trying to prove that if n is a natural number and 2 to the n minus 1 is prime, then n is prime. Now 2 to the n minus 1, if 2 to the n minus 1 is prime, that's a special kind of prime called a Mersenne prime, named for this guy, Mersenne, French theologian, philosopher, mathematician, and music theorist. So a man of many hats, and he worked with these primes that were of the form 2 to the n minus 1, and if you think about these kinds of numbers, again, n has to be prime in this case. You've got 2 squared minus 1, which is 3, followed by 2 to the third minus 1, which is 7, 2 to the fifth minus 1 is 31, and 2 to the seventh minus 1 is 127. So you can think about the prime numbers, 2 to a prime number minus 1, and I challenge you to think about whether that is always prime, if you take 2 to a prime number minus 1, when it is or is not prime maybe. But these are called Mersenne primes for this Baron Mersenne, who incidentally was friends with or correspondence with René Descartes. Etienne Pascal is the father of Blaise Pascal, famous for Pascal's triangle among other things. Also corresponded with Galileo. So all these people that in history and math, they have interesting stories behind the things that they studied, and I encourage you to look into those. Anyway, back to our exercise. We want to prove that n must be prime if 2 to the n minus 1 is prime. And you can think if n is not prime, for instance, 2 to the fourth. 2 to the fourth minus 1 is 15. Well, obviously that is not a prime number. So we want to prove that if 2 to the n minus 1 is prime, then n also must be prime. Again, not an obvious thing. So we want to look at that, and when I look at a proof like this, I want to think about the definitions. And the definition I see here is prime. What does it mean to be prime? Well, it means that a number is only divisible only by 1 in itself, or not composite. So it can't be factored into other factors. And so when I think about a proof, the first thing I'm trying to do is look at that hypothesis. N is a natural number, and 2 to the n minus 1 is prime. So I want to express 2 to the n minus 1 is prime mathematically, symbolically, algebraically. But that's difficult. How do I write that 2 to the n minus 1 is not a product of two factors? I'm writing something that is the negation of something that is easy to write. Well, that's a clue that maybe we might want to try to use the contrapositive. And the contrapositive in this case is, if n is not prime, then 2 to the n minus 1 is not prime. Well, I can write that n is not prime quite simply, right? The way I want to do that is to say that n is composite. And so to say that n is composite means to say that it's the product of two values. I'm going to call them a and b, where a and b are natural numbers. And significantly, a nor b can equal 1. Because if a were 1, then that would force b to be n, and in which case n might still be prime, because any number is factorable into 1 in itself. And so we want to force the issue here that a nor b can equal 1. But we've got two factors that multiply to n. Okay? So there's our setup. Now we want to see, where does this lead us when we look at 2 to the n minus 1. We've established the hypothesis, n equals a times b. Now we look at the conclusion. And so replacing n with ab, we get 2 to the n minus 1 is 2 to the ab minus 1. But I can rewrite that as a power to a power, right? So 2 to the a and then 2 to the b minus 1. And the reason I might want to do that is this last line here. 2 to the a to the b minus 1 to the b. Now, of course, 1 to any positive integer power is still going to be 1, and so I'm free to do this, right, because we've defined b to be a natural number. Now, why might we want to do this? This expression in this form might trigger something familiar to you, right? You've seen things such as a difference of two squares, difference of two cubes, and if you think about those types of expressions, you should realize something about them that is applicable in this case. Difference of two squares, for instance, is always factorable. x squared minus 4 is factorable to x plus 2 and x minus 2. X squared minus 64 is factorable to x minus 8 and x plus 8, right? It's always factorable to the first term not taken to the power minus the second term not taken to the power times something else, right? Well, it's no different here. By the factor theorem, which you may or may not remember, x to the p minus y to the p is always divisible by x minus y. The factor theorem states that if you have, if when you replace x, for instance, in a polynomial, let's call this x to the p minus y to the p, let's call this p of x. If we replaced x with y, then we would have y to the p minus y to the p, which of course would be 0. And so if y is a root of this equation, which it is, this expression, then x minus y is a factor, right? And that, that's very familiar to you when you look at something like x squared minus 4, right? 2 is a root of the equation y equals x squared minus 4, and so x minus 2 is a factor of y equals x squared minus 4. Likewise here, 2 to the a to the b minus 1 to the b is going to have a factor that's 2 to the a minus 1. And we'll talk about this factor theorem later in the year. We'll actually look at another proof of why this particular statement here is true. X to the p is divisible, x to the p minus y to the p is divisible by x minus y. But for now, we'll accept the factor theorem and notice that 2 to the a minus 1 is a factor of 2 to the a to the b minus 1 to the b. But we know a is a natural number that's not 1. And so 2 to the a minus 1 itself is not 1. It's an integer, it's a natural number greater than 1. And so we have a value, a natural number greater than 1, that goes into 2 to the n minus 1, that divides 2 to the n minus 1, and therefore 2 to the n minus 1 must be composite. And if 2 to the n minus 1 is composite, then we've shown that if n is composite, 2 to the n minus 1 is composite, which again is logically equivalent to saying if 2 to the n minus 1 is prime, then n must also be prime. And so again, we've used the contrapositive in a way that lets us prove a statement that might be a little bit harder to do directly.